Okay, you have arrived at Unit 2, Lesson 3. No Zumba music today, although I don't think it came through on the recording anyway, so sorry for that. You really missed out. You can see our objectives for today. We're going to graph piecewise defined functions. Sounds funky, but it's really quite straightforward. Shift graphs vertically and horizontally, and then we're going to reflect graphs. So we're going to be doing a lot of looking at graphs in this unit. Okay, I've already copied on here an example of a piecewise defined function for us to start with. When we say piecewise defined, all that really means is it's broken up into parts. And you can see the parts here. Let me choose my highlighter. The parts here are defined by, that is not my highlighter. I feel so lied to. It told me it was going to be a highlighter, but it's not. The parts are defined by the value of x. So if x is smaller than 0, or if it is equal to 0, then that means you use this equation. You use 2x plus 3 to figure out what your y value is going to be. But if x is bigger than 0, so in other words, if x is anything positive, then you're going to use this equation that I've got in blue now, the negative x minus 1, to determine what your y value is going to be, or your function value is going to be. So you can look over here at the graph and see what this looks like. You've got a split graph, basically, because you have two pieces. One piece is 2x plus 3, the other piece is negative x minus 1, and those two pieces do not meet up when x is 0. If, for instance, let's say, if right here at 0, when x was 0, if they had the same values, if negative x minus 1 and 2x plus 3 had the same values, then you would see these parts come together. But since they have different values at 0, which is where we're splitting from one line to the other, you see a little split here. You see this gap from there to there, because that's just the nature of the value of x. Now notice which point, where is x defined for 0? X is defined on this top equation for 0. So if x is 0, you don't plug it into the bottom equation. And if you come down here and look at the graph, let me get rid of my red circles, you see that there's an open circle right there. That one is an open circle. That tells you that point is not included. But up here at the top, it's a closed circle, which tells you that point is included. So this first line goes all the way up to this point right here where x is 0, and I'm selecting things unintentionally. And then the next line, then you at 0 you make this magical hop down here to negative 1, and from there on you follow this other line. And that's what the graph looks like. If you can split it up into two pieces like that, it's really not that complicated. You just have to know which piece you're on. So for instance, if I said, well, I want to know what is f, I don't know if I can write this, f of negative 1. Well, you can look at the graph and find it. If you go to negative 1, you go up, there's f of negative 1 right there. It's 1. Yeah, right? It's equal to positive 1, because the y value is 1. But you wouldn't have had to have the graph to know that. You could have just looked at our equation over here and you say, okay, x is negative 1, that is less than 0, so that means I'm going to use this top equation here. So I'm just going to plug negative 1 in right there for x. 2 times negative 1 plus 3. That equals 1. So that's where 1 comes from. Let me get rid of, I know I've got a lot of extra lines here. I'm getting messy. Clear my graph. Okay, well, let me come up with one that's not graphed for you there. Let's say f of 7. Well, if I want to know f of 7, first of all, I have to determine which line am I going to use. Well, since 7 is bigger than 0, I'm going to use the one I've highlighted in blue. All right, so I'm going to go to negative x minus 1, and I'm going to say, well, that would be negative 7. Minus 1. I'm just replacing x with 7, and so I get negative 8. And if we were to continue this line over here, if I came over here to the graph and continued it on, and we went over here to to 7, we'd go down and we'd find that point right there is at -8. So that's pretty much all there is to know about piecewise defined functions. If you need to graph them, then you need to graph them as two parts, completely separate. And I think all the ones you have will just be linear equations like this. So the main thing that you'll need to pay attention to that could get you tripped up is where is the open circle and where is the closed dot. So which point is included. So that's where you got to pay attention to this right here. I'm going to circle these symbols. You got to pay attention to which one has the or equal to on it. In this case, the top one did. It was less than or equal to. So that's why there was a closed dot right there and not down here, because that's just greater than, not greater than or equal to. All right, I think I have beaten that horse to death, so let's move on. And that was graphing piecewise defined functions. I really don't think you need more examples than that. Remember, if you're doing the assignment and you're feeling like maybe you're still a little confused, don't forget you can view an example inside of the assignment, and that's always helpful. Or you can do help me solve this on some of the problems. Okay. Last lesson we graphed some of the basic functions. Remember, f of x equals x squared. Some of the basic functions that are not linear anyway. The absolute value of x we did, and we also did the square root of x. All right, and those were pretty straightforward. Well, now we're going to take those graphs and we're going to move them around a little bit. So let's start with, let me pick out a winner for us here. We don't want to start out too complicated. Let's start with f of x equals x squared plus 2. Okay. Notice the only difference between this graph and the x squared graph is that we have a plus 2 being added on the end. Well, let's think about what that's going to do before we go to try to graph it real quick. Let's make ourselves a little table here, and let's think about what our values. Well, now what if x is 0? 0 squared is 0, plus 2 gives me a value of 2 for f of x. Interesting. What if x is 1? If x is 1, 1 squared is 1, plus 2 is 3. What if x is negative 2? We'll just go with negative 2, that's fine. Anything else won't fit. So, negative 2 squared is 4, and 4 plus 2 is 6. So if I come over here to graph this, here's what it's going to look like. I've got a point at 0, 2. I've got a point at 1, 3. I didn't put it on my chart, but I also have a point at negative 1, 3. If you'll recall, your parabolas are always going to be symmetric on either side. I've got a point at negative 2, 6. I'm also going to have a point at 2, 6. You can check that by plugging those values into the graph to see if you believe me or not. Okay, and there's basically what happened. There's what our graph should look like. I know my drawing isn't exactly perfect, but it's close enough. So what exactly happened? Let's compare this to f of x equals x squared. Remember, if I graphed f of x equals x squared, and let me do it in a different color. I'm going to do f of x equals x squared in red. Remember, we did this in the last unit, so you can go back and verify this if you need to. It looked like this. No, those are some bad points there. It looked basically like that. So what happened? What's the difference between the two graphs? Well, all that happened is we took f of x equals x squared and we shifted it up 2 units. Right? Each point, look at each point I've made. You just went straight up 2. The difference is 2. From there to there, from there to there, from there to there, from there to there. Any point I choose, I just go straight up 2 to get to the new graph. So this leads us to a nice convenient little rule. And the rule is, dun, 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 wait for it, wait for it. If you are adding or subtracting a number on the end, and this is true with the absolute value function or the square root function also. So if you take any of these functions if I have, let me just give you another example. If I have g of x equals, let's say, the absolute value of x minus 4. Well, all that's going to be is that's going to be the absolute value graph. So remember from the last unit, the absolute value graph was a V like this. And it's just going to take it and it's going to go straight down 4 units. So anytime you are adding or subtracting a number on the end, so out here, not inside of here, okay, not inside the absolute value or not inside the square part, but on the end, that's going to be a vertical shift. So a minus 4 means down 4, a plus 2 means up 2, just like it seems it would. So that is how we do vertical shifts. Now let's look at one that has a horizontal shift in it. I'm going to need to get myself some more space here. Alright, let's look at the equation. I'm going to use a funky letter just to throw you off, because that's kind of how I roll. P of x equals, I'm going to give you two things at once here. X minus 1 squared, all of that in parentheses squared, and then a plus 3 on the end. Okay, now notice I do have something being added on the end. I've got a plus 3 out here, and apparently I'm going to erase my plus sign in order to highlight it. I don't know why I would, but I did. I've got a plus 3 being added on the end. Well, that tells me that the graph is going to be shifted up 3 units. But now I've also got this going on in here. I've got a minus 1. Now, this is a horizontal shift. Like I said a minute ago, if you're adding or subtracting something out here on the end, that's a vertical shift. But if you are adding or subtracting something inside these parentheses here, or if it's absolute value, it would be inside the absolute value, or if it's square root, it would be under the square root sign, then that is a horizontal shift. So the only thing that might trip you up here is you have to think backwards on this sign. This minus 1 here is what throws some people off. Let me write it out in the rule form. If you've got, and I'm going to go back and use, we'll say this, we'll use P since I have P right here. If I have x minus h squared plus k, then my vertex of that graph is located at HK. There's the rule. Now I know that has a lot of letters in it and might look kind of confusing, but here's what we're saying. If you've got some number being subtracted from x in here inside the parentheses, then that number, not the negative, but that number itself is your x coordinate of your vertex. And then if you've got some number being added out here on the end, then that number is the y coordinate of your vertex. Here's how I think about it with the horizontal shifts, because the signs are backwards. I think, what value of x, let me use a different color to make it stand out. What value of x can I plug in right there and make the thing in parentheses be 0? Right? Since I've got a minus 1 on the end of it here, then I'd have to plug in a positive 1 for x to make the parentheses be 0. So that tells me I moved the vertex to the right, not to the left. So in this case, for P of x, my vertex is going to be at positive 1, positive 3. Because if this is a minus sign, what this is all getting at here, if this sign right here is a minus sign, that's actually a shift to the right, not to the left. I know on the end, if it's a minus sign, it means down. But when we're talking about horizontal shifts, if there's a minus sign inside those parentheses, that's a shift to the right. So if I go to 1, 3 and make a point, there's my vertex. And then from here, if I know what a basic parabola is shaped like, I can just kind of draw it from there. If you get the vertex in one other point, you pretty much have it. Especially if you're graphing it on my math lab, because all you need is a vertex and one other point, and it'll graph the rest of it for you. Okay. All right, let me look at one that is not. Let me throw it all together now. Well, I'll tell you what, let me look at one more. I'm going to look at one more on this graph before I move it. Let's say I gave you k of x. Let me do it in a different color. That's a bad idea to make it look like that. K of x is equal to negative x squared. Now, here's the deal. There's no shifting going on. There's nothing being added horizontally or vertically. So the vertex is at 0, 0. I'm going to put a green dot at 0, 0. But then there's this negative sign in front of it. This is where a reflection comes from. If the x squared term is negative, you've got a reflection. So now instead of opening up, this thing opens down and looks like this. Okay, so that's all you need to know for reflecting graphs. If you have a negative sign in front of the x squared term, or in front of the absolute value, or in front of the square root, then your graph is flipped. It's reflected over the x-axis. Alright, let's get a new graph, and I'm going to do one more, and then we'll be done. Alright, and this last one is going to be, oh, let's just use a good old-fashioned f of x here. F of x equals the negative absolute value of x minus 3 plus 2. Okay, so let's think about what we know. What we know is that the standard just absolute value of x graph looks like this. It's a V. It looks exactly like that. Well, pretend those were perfectly diagonal. I tried. Okay, so this is, I'll call it g of x. This is g of x equals the absolute value of x. That's what that graph there is. Okay? Now, let's think about how this one we have differs from that one. First of all, with the vertex. What does that tell me right there? I've got an x minus 3 inside of the absolute value sign. That tells me that I've shifted the vertex from 0, 0 to 3 something. That tells me I've moved the vertex to the right 3. And then this plus 2 on the end, remember that's a vertical shift. So that tells me I've moved the vertex up 2. So now for this graph, my vertex is at 3, 2, right there. And then the last piece of information I need to graph it. That negative sign out in front of everything. If there's a negative sign in front of the absolute value, just like if there's a negative in front of the x squared, that flips it. So now it's reflected and it's opening down. We haven't changed the shape. It's still going to be a V with perfectly diagonal sides. And again, you can start plugging in x values to make sure I'm not lying to you here, to make sure that these points are indeed all on this graph. For instance, let's just choose one. Let's say f of 7. Let's try f of 7. What would f of 7 give us? Well, it would be negative absolute value of 7 minus 3. Well, that was supposed to be an absolute value bar there. It didn't turn out straight. Plus 2. So we've got negative absolute value of 4 plus 2. Well, the absolute value of 4 is just 4. But then there's a negative sign in front of it. So this is negative 4 plus 2, which is equal to negative 2. So if I come over here to the graph and I go to 7 on the graph, if I go sideways to 7, 1, 2, 3, 4, 5, 6, 7, and I go down, I should be right there at negative 2, and I am. Well, assuming I drew a nice pretty graph, I am. My graph got a little wavy. But that is what you need to know. That is how we graph using horizontal and vertical shifts and reflections. You should be able to do all of the Unit 2 Lesson 3 assignment now.